Hey, this is part 5 in a series of eigenvalue inequalities, and it deals with the Brauer's ovals of Cassini. It's pretty unique inequality, and fun to review here. So let's let A be an m by m matrix, and then this is the row sum minus the diagonal element, and these were the Gershgorian sum, let's call it that, for each row. And this is reviewed more depthly in part 4. So an oval of Cassini it looks something like this, where it's the product of two numbers and then this ratio being less than that, and they create these crazy ovals. And it's not necessarily the oval that we think of. You know, it could be more like, you know, a figure 8 almost. It could be an oval, could be just two circles. Anyway, this is the ovals of Cassini, and Brauer uses this to put bounds on the eigenvalues of A. It's all, you know, called the spectrum of A, where he chooses these numbers using the row sums of the matrix, except for the diagonal. So let's look at that specifically. Here's the theorem, and it's pretty short. It says the spectrum is contained in these ovals of Cassini, created, you know, defined the way there. And matter of fact, and what this says, that all eigenvalues lie inside the union of these m times m minus 1 over 2 ovals. So let's look at a proof. So we have a matrix, m by m, the eigenvalues and the vectors associated with them. Each element of an eigenvector, for example, will be represented like this. So first eigenvalue will be xij for the jth element of that vector. And now let's look at this. So this is the first eigenvalue and eigenvector. And the elements of this vector can be ordered like this. There is a largest, and there's a second largest, and there's a third largest, etc. Okay, so if the largest is 0, then that violates this definition here. This has to be non-zero. So this has to be something positive. And then the second one, if it's 0, the second largest, then that means the eigenvalue ends up being that diagonal element. And so it sort of trivially holds. So for this proof, we're going to assume that these two are non-zero, the two largest. So let's look at the pth row of this matrix X. And now notice it's a p sub 1 and a q sub 1, because we're dealing with the first eigenvector. So the second eigenvector will have a largest element, and wherever that is, we're going to call it P2, and the second largest of this second eigenvalue will be Q2. So it'll be X2 Q2. So that's sort of the notation behind this. So we're looking at the pth row of the first, you know, when we deal with the first eigenvalue and vector. So this is this sum, and this piece is this. Remember, it's the pth row. Now, if we take out the diagonal element, that's when j is equal to p, and then subtract it to the other side, we get this. So that's this product here. It's a minus because it was a plus over here. Now, if we isolate this piece right here, we take that absolute value of it, that's equal to the absolute value of this side. So absolute value of this equal to the absolute value of that. That's true, and it's equal. So now if we take the sum but we move the absolute values in, this is greater than that. Now if this is for each element and we're on the pth row, so in this sum the diagonal element, the pp, is not there, and it's not here. So the next largest is the qth element of this. So let's set all these to the x1 q1, and that's what this is. So this is the next largest, so this is larger than that. Well, there's no index here, so it can be taken out of this sum, and this sum is the Gregorian row sum of the pth row, and then that's just the second largest element. So now if we divide both sides, oh no, that's it. So this is less than or equal to this. So now if we divide by this piece, this number, to both sides, we get this relationship. Okay, now let's remember that and look at the qth row. If we can go through this same thing, and then we could get this relationship. And so note that the p is on top and the q is on top. So if we multiply these two inequalities together, we get this times that is less than or equal to this times that. But this cancels with this, and we're left with this. So this is true. So the first eigenvalue is in this first oval of Cassini. Now we don't know what row and what row. These are two different rows that will be used, but we do know that these two, if we pick these two rows, then the eigenvalue will satisfy that. That's a fact. And then we could do the same thing for the second eigenvalue and eigenvector. We can go through that same algebra and show that the second eigenvalue has to satisfy this relationship. Now remember, this is P2 and Q2. So the pth largest value in this eigenvector, we don't know where it is, but it's one of the rows. And the second largest element in here it's one of those rows too. We don't know which one. So we can do this for every I. And so the statement is true. And what it says is that if we take the oval of Cassini for all possibilities, then the spectrum has to be within the union of all those. Now, it may be that we don't need certain of these oval of Cassinis, but we don't know that beforehand. So we union them all, which guarantees that the spectrum has to be in there. And that's what we just proved there. So now here's some interesting notes, is that in part 4 of this series, we looked at Gershgorian discs, and here we looked at the Brauer's ovals. And they use the same 2m numbers. They use the m diagonals and then the m row sums, Gershgorian sums. And then they come up with a method to estimate the spectrum, or the eigenvalues. So which method is better? Well, let's develop some notation first. So if we take the union of all the Gershgorian discs, we're going to call that G of A. And the Brauer's ovals, if we take the union of all possible, and then that's B of A. Okay, and the theorem says that Brauer's ovals are a subset or smaller than the Gershgorian estimate, and that's what we're going to show next. So let's let one of the eigenvalues be an element of this oval. And now remember that Oj is just one of the m times m minus 1 over 2 possible ovals. Now if Ri and Rj, remember these are associated with the I and the j, that means that lambda is the actual diagonal element. It's either this element or that element when one of those or both are 0. That has to be true. It's this or that. Which says, but if we know that AI is in the ith Gershgorian disk and this AJJ is in the djth Gershgorian disk, so that says that and lambda has to be one of those if Rj or Ri is 0 or Rj is 0. So that says that the eigenvalue is an element of this union. So it's an element of a Brauer's oval, implies that it has to be in the Gershgorian disk. Okay. So, but now let's assume they're both positive. Then that means this is true, because this, if we multiply that up, then this is the formula for Brauer's ovals. And now that being less than 1 says that, and remember that lambda is in this oval, so it satisfies this relationship. Now for this product to be less than 1 says that one of these have to be, or both have to be less than 1. Okay, so this has to be less than or equal to 1, and or this has to be less than or equal to 1. Well, that means that lambda is either in the first or the di sub Gershgorian disk, or it's in the second or the dj Gershgorian disk. And if it's in, and if it has to be in one of those, then it's clearly in the union. And so we just showed that the Gershgorian IJ oval is contained in the union of these Gershgorian disks, the Brauer's ovals in the Gershgorian disk. Now, this is true for all possible IJ. It's always in it's always a subset of this the union here, which says that the Brauer's ovals are always a subset of the Gershgorian disk. That's a fact. So the bounds on our eigenvalues are a little bit better if we use the Brauer's oval. And here's an example. And this is an example that we used in part 4. This is a correlation matrix, and we showed or noted that the eigenvalues are these: 0.36, 1.6, 1. The Gershgorian sums is 0.6, 0.8, and 0.2. Now, since this is a symmetric matrix, the eigenvalues are real, and we're really dealing with interval estimates, so it can be shown that the Brauer's ovals ends up that these are the left and right edges of that interval. Okay, easy to show based upon that relationship. It ends up, it's a quadratic form, and then you solve it. So this is minus b plus or minus, anyway, that. Now, so let's find the ovals for this matrix. So oval 1, 2, so that deals with the first row and the second row. Diagonal elements are 1 plus 1 over 2. 1 minus 1, which is there and there. And the row sum of 1 is 0.6. Row sum of 2 is 0.8. Now, if you crunch these numbers, we get an interval of 0.307 and 1.69. Then if we do the same with 1 and 3, we come up with this interval. 2 and 3, we come up with this interval. Now, a note is that, so if we take the union of these three, we get this interval. So this is the lowest there, and ends up, that's the biggest right there. And the eigenvalues have to be contained within this. And they are. They're, clearly within. But note that the union of these Brauer's ovals are a subset of the union of the Gershgorian disc, which we found to be 0.2 and 1.8. So a little extra work and you get better bounds on the eigenvalues, and see part 4 for this example. Okay, well, that's all I have for the Brauer's intervals of Cassini. Hope you enjoyed it. Please like the video and subscribe so you don't miss the next one. The next one's a pretty exciting one. It's called a shift estimate. I'll leave it vague like that. It's pretty neat. Very recent research. Not mine, but pretty neat. Talk to you later. Bye.